Section 4.6. Use a line to approximate a curve. Here we have a curve. It is the graph of some function f. Now, on the curve, I pick a point P, and I assume is x coordinate a. Because point P is on the graph of the function f, so y coordinate is function value at a. Then at the point P, I draw a tangent line. About this tangent line, I know point P on it, and also I know the slope of the tangent line. The slope of this tangent line is derivative at a. I know one point and slope, so I can write down the equation of the tangent line by point slope formula. Point slope formula is here. The equation of the tangent line is y minus y1. y1 now is y coordinate of point P, f of a. It's equal to slope derivative at a times parenthesis x minus x1. x1 is x coordinate of point P. I move this number f of a to the right side, then I get this equation, tangent line equation. This part depends on x. This part depends on x. It is a function of x. I name this function as L of x. L means a line. A line. Okay, now I pick a second point on x-axis. I pick a second point x on x-axis. Corresponding to x, on the curve, there is a point Q. Y coordinate of point Q is function value at x because Q is on the graph of f. Corresponding to this x, on the tangent line, there is a point R. Y coordinate should satisfy the tangent line equation because arrow is on the tangent line. So y coordinate satisfy the tangent line equation. So it is y coordinate is this. Okay, now from this diagram, it's easy to see that when A and X are close to each other, point Q and point R will be close to each other. Therefore, their y coordinates are close to each other. Now, from this observation, we have the following approximation. This approximation. Yeah. The both sides of this approximation are the y coordinates of point Q and point R. Yeah. In this approximation, left-hand side is function or a curve. Right-hand side is a tangent line. Tangent line is a line. So actually, in this approximation, we are using a line to approximate a curve. The board calls this approximation the tangent line approximation of the curve at the point A, or the linear approximation of the curve at the point A. This approximation is good when x is near A. However, when x is far from A, this approximation is not accurate. This is easy to see from this diagram. When the 2 points are far away from each other, point R and point Q are far from each other. Therefore, their coordinates are far from each other. In the following, I will show you examples about how good this approximation will be, and also some examples about how we use this approximation to solve practical problems. Example 1. Consider this function and the point A. Point A is 1. There are several questions. The first question, write the equation of the line that represents the linear approximation to the function at the given point A. The line that represents the linear approximation at the given point A is the tangent line at the point A. So this question is the same with the question. Write the equation of the tangent line at the point A. At the point A. Let me plot the graph of the function and the tangent line. Yeah, the function is, this is the function. The domain of this function is any number between -3 and infinity. A function only has graph on its domain. So the graph of this function is this blue curve. Point 1 is here, A is here. The point on the curve, the corresponding point on the curve is xy coordinates are 1 and function value at 1. Function value at 1, plug in 1 in x here, then function value at 1 is 2. Square root of 4 is 2. Okay. Now to write down the equation of the tangent line, I need to know the slope of the tangent line. I have 1 point. I need to know the slope of the tangent line. For the slope of the tangent line, compute derivative. Okay. The function is square root of x plus 3. In power, it is x plus 3 to 1/2. Now, take derivative on this function by chain rule. Yeah, this is a chain rule. So I get the result here. X plus 3, derivative is 1. Derivative at 1, plug in 1 in x, then I get 1/4. This is the slope of the tangent line at 1. Now I have slope, I have 1 point on the tangent line. By point slope formula, I can write down the equation. Yeah, this is a point slope formula. Yeah, this is a y1. Y1 is function value at A. This is slope of the tangent line. A is 1. Okay, so plug in 1 here. Yeah, function value at 1 is 2. Derivative at 1 is 1/4. Simplify this expression, then we get the tangent line equation here. This is a A. B, question B. Graph the function and the tangent line on the same set of axes. I'm done here. This is the answer to B. Still example 1. I copied the questions here just for the convenience of my presentation, so that I don't need to move back to the previous page. Okay, now question C. Use the linear approximation to estimate the function values at point 98 and at 1.05. The linear approximation formula is here. The left-hand side is the curve, the function f. And the right side is the tangent line at the point A. This approximation is good when the 2 points x and a, they are close to each other. In this example, the function f is this square root. So I plug in this square root in f here. The right side is tangent line. We got the tangent line equation in part A. So I plug in the equation here. So we get the linear approximation for the function in this example at the point A. The point A in this example is 1. So the linear approximation of the function, this function at 1 is this. This approximation is good when x is close to 1. Okay, now to estimate the function value at 0.98. Now I set x to 0.98 and plug in 0.98 in x here. So we get this approximation. By calculator, this sum is this number. This number is an estimate of this square root. How good this estimate is let's compute the exact value of this square root by calculator. This is the exact value. Now compare the estimate to the exact value. We can see that they are very close. But still, the estimate slightly larger than the exact value. In this case, we say that the estimate is an overestimate. Similarly, to find an approximation to the function value at 1.05, we set x to 1.05, then plug in 1.05 in x here, Then we get this approximation. By calculator, this sum is this number. Okay. And also we use calculator to compute the exact value of this square root. Yeah, exact value. Now, the estimate, yes, is indeed very close to the exact value, but still overestimate. The estimate still slightly greater than the exact value, so overestimate. This is a part C. Part D. Compute the percentage error in your approximation in part C. Okay. The percentage error formula is approximation minus the exact value, then divided by the exact value. Actually, this is the relative error. Okay, now let me compute the percentage error for this estimate first. By formula, estimate minus exact value. Exact value is this. Then divided by the exact value. It is this number. And translate this number into percentage. Then we get the percentage is this. Percentage is very small. That means that the estimate, this estimate is very good. This is a very good approximation to the exact value. For this estimate, similarly, we can compute its percentage error. The answer is this, and also very small. This is a part D. Now, part E. Based on the graph in part B, state whether these approximations overestimate or underestimate. The graph in part B, okay, move back. Yes, yeah, This is the graph in part B. From this diagram, we can see that the tangent line is above the graph of the function f. So when we use the tangent line to estimate the graph, the curve, the estimate should be overestimate. Here, this is the answer to part E. From the plot in part B, we see that the tangent line lies above the curve, the graph of the function f. So our estimate in part C, yeah, 1.995 and 2.0125 estimate in part C. So our estimates in part C are overestimate. This is a E. Question F. Compute second derivative at A. Now A is 1. Compute second derivative at 1 to confirm your conclusion in part E. Okay, now compute derivative twice, okay? Compute derivative once, we get the result here. Take derivative on this guy again. I use chain rule because this function is 1/2 times x plus 3 to negative 1/2. I use chain rule to compute it. Then I get the second derivative is this. Now compute derivative at 1. So plug in 1 in x here. Then I get the second derivative. It is negative 1/32, less than 0. Recall that second derivative is about concave up, concave down. Second derivative less than 0, that means that the curve, the graph is concave down at the point 1. Yeah. This blue curve is the graph of the function. At the point 1, the graph is concave down. Second derivative less than 0 at 1. Concave down at 1. Because the graph is concave down, therefore the tangent line at 1 lies above it. So tangent line, use tangent line to estimate the graph. The estimate is overestimate. This is confirmed. Part E. Because second derivative less than 0, so the graph of f is concave down at 1. Therefore, tangent line is above the curve. So the approximation in part C are overestimate. These are the solutions to this example 1. Now we turn to example 2. Second example today. Use the linear approximation to estimate the following quantities. Choose appropriate A and the function f. Recall that the linear approximation formula is this. Left-hand side is the function f, or the curve, a curve. The right-hand side is tangent line to the curve at the point A. When the 2 points, x and A, they are close to each other, this approximation is very good. Very good. Okay, now to approximate this number to use the linear approximation formula, we need to determine A and the function f. This quantity is some number to the fourth. So I choose the function f to be x to the fourth. And x, what is x? I need to choose a number for x. I pick 1.999 for x here. Then what is a? A should be close to x and easy to evaluate at a. So I pick 2 for a, 2 for a, 2 for a. Okay, now I have the function f and the point a. Now let me compute function derivative at a. Take derivative on the function. Then I get 4x to the third. Now plug in 2 in x to get function value at 2. 2, right? Plug in 2 here. 4 times 2 to the third. It is a 32. 32. Okay. Then the linear approximation formula now becomes, okay, function x to the fourth. Function value at a at 2. Function value at 2. It is a 16 plus 32. 32 times x minus 2. Yeah. This approximation is good when x is close to 2. When x is close to 2. Okay. Now, I set x to 1.999. 1.999. This number very, very close to 2. Plug in this number in this approximation, then we get this approximation. So this number is an estimate to this quantity. Actually, this number is the answer to the question here. How good this estimate is? Let me compute the exact value of this quantity by calculator. Exact value is this. Compare the approximation to the exact value. We see that they are very, very close, very, very close. But this time, this estimate is an underestimate of the exact value because the estimate less than the exact value. Underestimate. Okay, now second quantity. Okay, first by calculator, 5/19 is this number. Yeah. Okay, now to use this formula to estimate this quantity, we need to determine what is x, what is a, what is the function f. The function f, I choose square root of x. What is x? X should be this number. This is x. Yeah, this is x. Now, what is a? A should be close to x. And also, function value should be easy to evaluate at a. So, a close to this number and easy to evaluate at a. I chose a to be 0.16. 0.16. Yeah, 0.16. 0.16. Yeah. Function value is very easy to evaluate at 0.16. Okay, now to use this formula, we need to compute derivative at a. Derivative of the function at a. Take derivative on square root of x, then we get this. Now, plug in a, plug in 0.16 in x, then we get this. Square root of 0.16 easy to evaluate. It is a 0.4. So it is a 2 times 0.4, 0.8. 1 over 0.8 is 1.25. Okay, now with all this information, the linear approximation becomes function is square root of x. And then function value at a, square root of 0.16, 0.4. And then plus derivative at a, 1.25, then times x minus a. Yeah, this is the linear approximation of square root of x at the point a. A now is a 0.16. Okay, now in this approximation, we set x to be this number, 5 over 29. Yeah, 5 over 29. Okay. Now set x to 5 over 29. Then we get this approximation. Calculator for this sum. Then we get this number. This number is the number that we use tangent 9. This number is from the tangent 9. Okay, it is an approximation of this quantity. How good this approximation is? Let's compute the exact value of this quantity. It is this number, exact value. Now compare the tangent 9 approximation to the exact value. We see that they are very close, but the estimate, the approximation is slightly smaller than the exact value. So therefore, slightly greater than the exact value. This is a 4155. This is a 4152. So this estimate is an overestimate of this quantity.